Welcome back to our NavMesh controller series. Last time, we built our foundation. Now we're adding some new tools to the kit. First, we'll set up a simple camera system that just follows the player around. Nothing too fancy yet, but enough to keep the action in view. Then, we'll change how the controller handles rotation. Instead of always turning based on movement, we can make it face a target when it's nearby, or work with a lock-on system. We'll also make our controllers bump into each other instead of passing through like ghosts. And finally, we'll build a prediction system that calculates the controller's future. Later in the series, we'll use this to smooth out movement and animation, but for now, we'll focus on getting the core mechanics in place. Let's get started. We'll start by creating a look-at-object script with a simple on-trigger enter and on-trigger exit setup. When the player enters the trigger, it will tell the controller to start looking at a target. When they leave, it'll stop. While we're at it, we'll also add a look-at function inside the controller script that swaps out our normal rotation logic with one that forces the player to face the target. Now we can quickly set up our look-at-object in the scene and give it a quick test to make sure everything's working. Perfect. Before we move on, let's rename our test script to Game Controller so the name actually matches its purpose. Next, let's create a simple camera follow script so the camera can track our current controller. We also add a function to the camera controller that lets us change the follow target whenever necessary. We also need to set the initial controller as the camera's target when the game starts. While we're at it, let's update our switch chars function so it changes the camera's target whenever we switch to a different controller. Before we move on, let's update the handle input function so the movement directions are relative to the camera's orientation. All that's left now is to quickly set up the camera controller and put it to the test. Perfect. To make our lives easier, let's create a ControllerData ScriptableObject. This will store all our controller's parameters in one place, making them easier to tweak and giving us more flexibility down the line. To address our controller collision issue, let's start by creating a new character layer and assign both controllers to it. Then, we'll add a NavMesh agent component to each controller. This will prevent them from overlapping, as they'll push each other aside. However, this alone won't fully solve the problem, since it doesn't affect their movement speed. It just makes them collide physically. We need to add a collider to our controller and set it as a trigger. We also need to update our collide and slide function to detect other controllers using physics spherecast, much like how we used NavMesh raycast earlier in the series. This allows collisions to properly affect the controller's speed. If the controllers are still pushing each other around, we can either increase the spherecast radius or decrease the NavMesh agent's radius, whichever works best for your project. Now it's time to build our prediction system so that we can later use it to smooth out movement and animations. First, let's add some helper variables to make handling our gizmos easier. Let's also set our input and movement gizmos to only show when the corresponding helper variables are toggled on. And let's also add an onDrawGizmos function to draw spheres at the start and end points of our predicted path. We also need a vector3 variable to store our input, so we can use it inside our prediction loop. Now we can build the foundation of our prediction system. First, we define our starting values. Then, we add a loop that simulates future frames, computing the input by smoothing the target input just like we do in the handle input function. To keep things realistic, we'll clamp the magnitude of the smoothed input so it doesn't exceed 1, which can happen because we increase the timescale each frame. Keep in mind, the further into the future we predict, the less precise the simulation becomes. We also need to update our collide and slide function so it returns true when an obstacle is hit, and false when none are detected. This will come in handy later on. And again, we're halfway there. Time to sip some coffee or tea and take a break. Stretch your legs or do whatever you need. You do you. Or hey, just keep going like the crazy tutorial watching champ you are. We can now compute the velocity for the current frame, just like we do inside the movement function. To make testing easier, we'll draw gizmos to visualize the velocity for each simulated frame. Then, we simulate moving the controller exactly the same way as in the movement function, sampling the NavMesh position to ensure we have a valid position for each simulated frame. Finally, we set the predicted end position so we can visualize it properly with our gizmos. At this point, our prediction function should look like this. Just to make our lives easier, let's make the gizmos only appear when their corresponding helper variables are toggled on. Before we test our code, let's make sure to call our prediction function inside the handle input function. As you can see, our controller can now predict its future position based on the current player input, assuming the input stays constant. Now, let's use the prediction function to directly influence our controller's movement. First, we need to create a vector3 variable to store our predicted input vector and initialize it to the target input before the prediction loop. This will come in handy later. Once the loop finishes, if the controller was receiving input, we update the input using the final predicted position. We'll develop a more refined method for this down the line, but for now, this approach will suffice. Now, we can use the predicted input vector inside our handle input function to compute the smoothed input. As you can see, the movement is already a lot smoother, but it's not perfect yet. There are still some issues. For example, I'm not actually changing the input here. The controller is just trying its best to move based on the predicted input, which causes it to move around instead of staying put in the corner. To address this issue, let's keep track of how many frames have passed since the simulation encountered an obstacle, and if enough frames have passed, we break out of the loop. We also need to track whether the controller ended the loop colliding with something. By doing this, we only use the predicted data when the controller is about to slightly graze an object. This way, we're not taking control away from the player. We're simply helping the controller avoid corners and bumps, making the entire experience feel much smoother. Think about it. If you were running toward a corner, you'd naturally shift a little to the side to avoid it. Otherwise, you'd hit the corner and jitter as you try to push past the collision. We can also adjust the simulation length, making it longer or shorter, depending on the specific use case. The final topic we'll cover in this part of the series is checking if the controller is about to hit his head on something. I know he doesn't have a head yet, but in the next part of the series, I promise he'll get one. Let's start by adding a check radius and a layer mask alongside the controller height in our ControllerData ScriptableObject. Let's also add a vector3 helper variable that we can use inside our onDrawGizmos function to visualize this mechanic. While we're at it, let's set it to a default value like we did with the predicted start and end points. Let's also add a crouch distance variable inside our prediction function, which we can later use for IK. Finally, we can add a sphere cast inside our prediction loop that casts upward to check for objects at head height or lower. This lets us track and visualize the lowest point overhead. Later in the series, we'll use this point to determine how much the controller should crouch. There you have it. In the next part, we'll tackle adding a character model, animating it, working with inverse kinematics, and updating the prediction system to make it even better. Plus, we'll share ideas on how you can further improve the system based on your specific needs. As always, all the relevant project files are available on our Gumroad page, and since making this video, we've also uploaded them to GitHub. It's completely open source, so feel free to use it to your heart's content. We'd love to see what crazy things you create with it, so don't hesitate to share your updates with us. For the Blender artists who just want to play around, we'll also create a video showing how to import the project files into a Unity project, so you can use them right out of the box with minimal hassle and no coding required. Cheers, and see you next time.